Right, share. All right, so we are recording now. Okay, so this is the second half of today. We can take a look. Let's see. Training is almost done, I think. Just 2 more iterations. So let's actually see it finish, and hopefully, we'll get better numbers. And then we will, oh, it finished. Perfect. So it did these from 0 to 29, 30 iterations of training. So now let's go here. Let's run the, oh, okay. So that's weird. But, so you can see that's neural networks for you. They do weird things. Let's see here. It got, it's probably been collecting. Oh, I see what happened. It's because I started it again. The list captured the beginning. So it's basically this part over here. You see that? But then it became optimized because I didn't flush out the old one. But such, hopefully it should be fine. All right, so let's see if we can generate some random images. Okay, so shapes. Okay, that looks better. How about this one? Ah, okay. Better, right? A little bit better. What number do you think that is? 6. I say it's an 8. An O with an accent. All right, let's try this one. 2. That's a 2, right? So these are definitely a little bit better. This one was terrible. Right, so let's see how it looks like now. A 1 or a 9, maybe. How about this one? Okay, those look very similar. Okay, not so great. Not so great. So as you can see, it's a bit of a challenge, right? That's a terrible one. Let's try one more. Come on. I don't know. Okay, might be because the model stopped and then I continued it. So definitely, but as you can see here, some of the numbers were good before. All right, so the next step that we're going to do now is I'm just going to reuse the same code, but now I want to generate conditional images, right? So I'm going to be using this script over here. And and so my goal is going to be, if I want 9s, I'm going to generate 9s. If I want 3s, I'm going to generate 3s. If I want 1s, I'm going to generate 1s. All right, so I need to provide the condition basically for this, 4s, etc. All right, so let's start, run generator after training. So we are going to basically do something like this. I'm going to copy this, but we're going to need to make some changes to our neural network. So actually, maybe I'm going to rename this. This one is already, you already have this one, right? So let me rename this. CGAN. Okay, so I'm going to rename it. I'm going to add a few cells in here. So I'm going to do inference CGAN. Markdown. Okay. So hopefully we just have to make a few tweaks. Basically this, we tell it the label that we want. We can initialize a torch tensor of size 10, right? Of all zeros, basically. So notice it's all zeros. That's the label tensor. And then we just say on the specific index that we want that value to be a 1. Does that make sense? So we can take a look at it here. So I'm starting with this so that this kind of guides what changes we need to make to our network, right? So let's go ahead and print this one. So if it's a 9, right, it gives us something like that. So the last one is the one hot encoded vector. This is the condition that we're going to put in, okay? into the GAN. The GAN is the one that gets this information. All right. We may also need to provide this to the discriminator in some way. So we're going to take a look at that. Okay. And then here, this second part is just basically creating a plot. And then we're just going to generate several images conveniently. So here, notice we're going to use the generator. We need to provide the generator random seed, which is still going to be the vector of size 100, but we also now provide the label tensor. All right. These two parameters are going to be passed to our generator, and then it's going to generate our output, which is going to be the image based on that condition. And then basically the rest is just reshape, detach, and add the images into this plot, and then we should be able to get it to work. Got it? All right, so now we need to think about passing this to our GAN generator here. So we have generator net, which takes in, this is the generator, right? So we've got our forward function, and we need to make that modification. So before we were just passing it the random input, right? So now we need to, oh, this is the deal net, sorry, this one. So forward. So let's take a look. G forward takes two parameters, label tensor, one hot encoded vector. Here, right? So then, like that. Does that make sense? Okay, so we need to now think of the architecture also. So this was 100 by 256, and then 256 to 784, right? Do you guys see that? Yeah. And so we have now 100 noise, but also 10 for the label. That's where this 10 is coming from. Okay. So that means that what goes in here, let's say input vector, needs to be what? Rand input plus label tensor. We need to concatenate those two together. And that will become the input that goes in here. And that's going to be reflected because this is 100 by 10. Make sense? All right. So this is what we need to make happen here. Well, these are just the generations. 1, 3. Okay. These are the plots. Okay, so this is just a training here that I have. Okay, so detrain. Yeah, so now the discriminator also is going to need the target tensor. Random one hot. Okay. So we need a function here. Generators. So there's the architecture 100 by 10, 784. Forward takes this, and here we go. So this is what I was looking for. Okay. So we need to input vector torch cat, and we're going to basically use this, the label tensor and the random input. So I'm going to plug this one in here. Okay, and label tensor I already have in there. And I'm just going to call it input vector, or inputs, actually, it's good. So then this should be inputs, right? Do you guys see that? Make sense? Now, the key thing is that the discriminator also needs to learn to discriminate based on the conditions, so we need to account for that. Okay, so notice here we just concatenated, that goes into the input. Discriminator needs to take also the image and the label tensor. Okay, so that should be good. So now let's take a look at all right, so here's the discriminator class. So notice that the discriminator class is still producing real or fake image, but we're going to provide the one hot encoded as an input. Here we have the image plus 10 for the label vector. Okay, so we need to define that in the architecture. So we're going to go to the discriminator here, plus 10. You see that? Okay, so we're going to provide that in there. And we probably need to perform that operation, the concatenation. So, look. All right, that's the model. Forward, here it is. So we provide image tensor and label tensor. So I'm going to copy this one. Okay, so this now takes label tensor just like that. Okay, and this is going to be X, the image, and they just get concatenated. Okay, because it's a 784 plus 10, right? For the discriminator, that's going to be called inputs. So then basically this one should be inputs like that. Any questions? So I'm trying to keep this pretty simple. Okay. If you notice here, we need to provide inputs and the label tensor. It's just the losses, the loss function. Yeah, that should be it. And then, of course, we will need a few utility functions just so that we can, let's, you know, maybe we need some utility functions. So I'll come back to that. Yeah, I'm pretty sure this is just loading the MNIST data set, so that's fine. So, all right, so let's take a look here. What do we need? Generate random, we already have that. Generate random image. Random seed. And a random one hot encoded vector probably. Okay. Put this in here. Okay, so this will just take a label or size 10 here, generate one hot encoded vector, and randomly creates a one hot encoded vector basically. Okay, so let's have that. All right, so now the architectures are defined. So now the problem is going to be in the training function, right? So we got to make some changes here. All right, so what do we need to provide here? We need the labels, so that's another thing here. Okay, so let me gonna print YB. Okay, I'm gonna put an input here. Okay. All right, let's go ahead and do that. Okay, do we have labels for the images? We do, right? If I do, these are the labels basically. So we do have the labels in there, so that's good. And they're in YB. So I'm gonna kill this one. So now, hopefully, we just have to modify this function to account for the labels. So let's think. We get the XB, we have the label. We generate random batch vector, comma. The model needs the labels, correct? So what do we provide here? Model. So let's take a look here. Generate. Should it be a random label? Trying to think. Random. Generates a 7. Should learn to generate 7s. So that's really the hard part here to figure out, right? So target tensor. Okay, so the one thing we do know is that in the training function for the discriminator, these are real images, so probably we need to provide the real labels, right? So then those go here. So X, this is the real data, and so this should be YB. Do you see that? So we provide the real images and the real labels to the model, right? And it should learn. It gives us predicted, whether it's a 0 or a 1. Okay, so I think that's correct. Now for this one, or it's basically, we give it some label. So I think this should be a fake set of labels. So we need a function for that. So this generates random one-hot encoded vector, but we need something of batch size, right? So how do we do that? So if you notice, this one, so here's the dtrain, gtrain. Okay. So we give it real image, real label. Because target tensor is coming from MNIST dataset. Image data tensor is also coming from MNIST, right? So this is real. Dtrain with the generated image gets what? Random label and random label in there for the generator. Do you see that? Do you agree? And then in the GAN here, random seed, random label. That's it. Right? So the thing that we need to then provide is we need something to generate random labels, but of batch size 64 or 32. So I don't know that I have that function here. I have generate random one hot. But I need. Where? Yep. Yeah. Is it the batch size? Torch zeros. I think this is 10 though. I think it seems to be 10. And then this is just the ID. So this only does it for one. So, right? So I need one that does it for the whole batch of 32. Do you see what I'm saying? I think because you can't provide. So it's like it's you think of how it is, right? You give it the noise and then you give it a 7, or you want a 3, or you want a 5, or whatever you want. And then the GAN needs to learn to generate, given that noise and that 3, a 3. Or if you give it a 7 and that noise, a 7. It needs to generate that. So the trick is we need to build one for batches. Now, in the code I had here before, I did this. So we just got to modify this, I think. All right, so let me do this, right? So add a cell. So generate batch and one hot. Let's call this one. Generate batch random batch one hot. Right? You guys can help me. All right. Feel free. All right. And then we just need, you get what I'm trying to do, right? So it's basically like this one, but I need it to be a batch size of something. So this generates, so I could do possibly 10 here. It's a similar idea to this one. But I need to have some of this in there. I need to provide the random ID. So this provides one ID. I need 10 of these randomly generated, right? So maybe this is inefficient, but for I in range, that's going to be pretty slow, I think. We have to do this for every thing. And then, right, that's the, it's for batch size, isn't it? Okay, so we generate the random and then rand vector. Right? And we need to provide I, comma, like that. Joey, come on.
It says torch.rand, would you do torch.zeros? Like if you want to do 1.5.
Yes, that's a good one. Good catch. Zeros, right? Yeah. So this creates, good catch, right? So zeros, batch 32 by 10. For each batch size, I need to generate a random ID. And then I'm, each of the, and then provide a 1, right? Looks about right, I think.
Yeah, you might have to permutate it or something, but.
Why? Why?
I'm not sure if it's I comma, if it's like, if you want to do backside comma 10 or 10 comma backside.
I want to do
It's,
3 and then on the column side, just put it, well, we can actually test this out.
yeah, you can just,
Let's take a look. All right, so let me run this one. And then I'll view it. Right, and then let's invoke it. So we just need to provide to this the batch size, I guess. Which is, yeah, batch size. Batch size. And then here it would be 32, let's say. Take that out. This returns labeled tensors. So.
Both lines.
oh, yeah.
Random batch.
Oh, size.
That would be 10.
That would be 10, yeah. 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 That'll work. So then this would be 10. Yeah. Okay. Right. See if it works. Nope. Name random is not defined. Didn't I use it? The same function, isn't it? Okay, so maybe I just need to run all these again. There's no random. Oh, it's, yeah, I can see that. It's because this used torch ran here. Torch zeros. Import random. Okay. Huh. The vector is not defined. Oh yeah, vec. Okay. Yep. Vec. Let's try that one more time. Okay, okay. So this gives us a batch of 32 with just random numbers, correct? Random one-hot encoded vectors. Okay, does this make sense, guys? So we have a generator. We give it this one plus the noise, and it should learn to do what? A 0, 1, 2, 3, a 4. Right, in theory. Okay, so this is basically, so we have a function, random one hot, that we can use, and that's a torch tensor. So the trick is here, right? So we provide, so going back to this one, we have real D model. We need to provide something here, which is the generated image. And it's a batch, 784. And so actually, they don't. This is one. Labels. Right, like that. And then for the generator, also gen labels. Okay, yeah, I think I didn't define everything. All right, so let's try it. So the board is missing one label tensor here. There. Do you guys see? Let's go back to this code over here. And let's just kind of dissect it. We're missing something here. All right, so this is the other, I could have done this example, but I was trying to keep it consistent with the other one. They're similar. I just happen to like the other one a little bit better. But they're essentially the same. So let's think this through and let's see if we can find the bug. So CGAN MNIST, right? We got the libraries. We've got the data, this is just getting the MNIST data in a different way. Okay, so convert data to tensors. We're going to have to read this whole thing. So let's see. We read in from a CSV, data frame. Just drop like the index and things like that. We're going to have labels, tensor images, and the one-hot encoded version of the labels, right? So we need to, it's really a conversion thing. This is one-hot encoded. This is a 7. This is a vector with index 7. Number of samples is 6,000. It's the length. Okay, then we have this one, convert data to tensors. Data. So we iterate basically. Yeah, it's a for loop. So I think the difference between this code is that this is doing on a per item and the other one is a batch process. Yeah, that not a one-hot encoded. I know, and so you gotta help me to fix that, right? So they're a little bit different. So essentially they're the same, but they got differences. So this is index 0 here. That's the label, the first one. And then that gets torch zeros, becomes the target. So it is one-hot encoded, right? And so we have a version that is the number and another version that's the one-hot encoded. Then we have the image, convert it to float, normalize, all that. And we have this list. One is the label, one is the one-hot encoded version of it, and one is the image. Everyone with me? All right, so, okay. This plot, I'm pretty sure we can ignore. So this just reads the MNIST data from CSV. And then we can plot 17. There's the data. And we can view it, and it's an 8. Okay. So hopefully that doesn't affect anything. Invoke, convert data to tensors. Now we have our 3 lists. So the label, the one-hot encoded version of it, and the images. Okay, so let's look at these random functions. Generate random and generate random image. So one just does rand size, random data. So it can be any random of any size. And this is torch rand size. So they're basically the same, unless you guys see any difference. But probably that one you're using to generate a 784 and the other one a 10. Random seed, that's basically for the generator. So that's going to be like 100. So again, pretty much the same function. Generate random one-hot. So this size here must only be an integer. So we do torch zeros, size 10. And then we pick a random number, rand index, and then that's kind of what we were doing with the batch, right? So label tensor. So I think we get that. Discriminator, okay. Initialize it. This uses a different approach, right? So the other one. But what matters here is the architecture, right? So this is the discriminator. The discriminator takes images, right? So this image is 784, but now remember, we're concatenating the label to this discriminator. Now it's not learning to say it's a 7 or a 6, but it's learning still to say it's a real or a fake, right? But, you know, we add it here. Then we have a hidden layer of 200, leaky ReLU, and once again, it just predicts a neuron of 1, which is sigmoid, to predict whether it's fake or real. So that is clear. Same BCE loss, that hasn't changed. And the atom optimizer is in this class, but it takes its own parameters for the discriminator, and that's the optimizer, and then a counter here. Then we have the forward function. This is critical, so this is really important. This invokes the model itself, which is this one over here. So the neural network architecture, okay. But it takes as input 2 things, the image tensor and the label tensor. I'm almost 100% that this one only does 1 image and 1 label at a time, right? That's what you guys see also. Yeah. So whereas the other code example uses batches, and I think that's what's causing the problem. So image tensor should be 784, right? And this should be 10, correct? Yeah, that's what I'm believing, which is consistent with that. So then we concatenate both of them. That's basically it, right? So when we do the concatenation with batches, we got to be careful also that we get the dimensions correct. So this is probably 1 by 784 and 1 by 10. And the other one would be 32 by 74, 32 by 10. Do you guys agree? Label tensor sometimes for the discriminator will take real data, sometimes will take fake data. But I believe this part we've got right. So the key thing is torch cat, and to write, I've already written this. And then that just goes into the model, and that's it. So I think we're good there. Then the train is here, and that's what I didn't like about this code. Is a little bit too. So, but in the train, basically, it takes its inputs, label tensor, and the targets. Okay, so this takes train, inputs, label tensor, the actual label. So now calculate the output of the network. So it invokes forward. Oh, okay, so it invokes forward and it provides, we know that this is the image, right? So that's inputs. Okay, this one. So this is the images, right? And then it also provides label tensor, that one, which is the vector, right, of size 10. Or maybe a label. So that's the one thing we have to get right. So that goes into forward, which goes here. Okay, and then it invokes the model. So that produces the outputs. Then we just invoke the loss function, outputs versus targets. That's the loss. This is just a counter, so none of this is relevant. And then we just do the optimization. Got it? Everyone with me? So that's where we, I don't see anything that, so this is the structure of the discriminator. Remind me, it takes the images and labels. Progress, this is, we don't need that. Test the discriminator here can separate real and random noise. So we don't need this. This is just an example. But you can see here it takes detrain. So it takes image data tensor from MNIST, a real image, target tensor, a real label, which is one hot encoded, right? One hot encoded. And once again, we give it the label 1. And notice this is just a torch flow tensor 1 instead of being a matrix as we did before. Does that make sense? So that's a real image. Then we use generate random image. So this is fake. Random, generate random one hot encoded, and it's a 0. So for the discriminator, we give it either a real image and a real label of size 10, or a fake image and a fake label, right, of size 10. Yes? Okay. All right, so this is where we need to, but this is still the same thing. And that's just running that example. Manually run the discriminator here. So forward, image, data tensor, and real. Okay. And it'll predict. And then if we give it it's going to predict that it's real. So it learns. If we give it a fake, then it predicts it's fake. Okay. Now the generator network, 100 by 10, 200 to 784. Okay. Torch optim. These are the parameters of the generator. I just think this is more complicated to grasp. So then we got the forward function here. Let's think about, because this is actually quite important. We give it the seed, which is the vector of 100, right? So that goes in here. We also give it the label tensor, and that needs to be concatenated, right, in the generator. And that becomes the input to the model. So 100 by 10 for sure. So the question is, this is probably a random. Both of these are a random, what I think. This is just a discriminator for the loss, inputs, label tensor, and target. So here we have inputs is the 100 vector. Label tensor is the 10, and that gets concatenated. G out. And then that G out goes into the forward, and the key thing is it's got to be the same label tensor that went in here, okay, in both. So it goes into the discriminator. The output then is loss function, the out to the targets, which is this one over here. So we just got to see what we give it in the training and the actual training. And then that's just the loss and, 0 out the graphs. Got it? All right, so plot, that's not relevant. Plot images, that's not relevant either. Everyone with me? Okay, so now, and then here we can see an example of how to use the G forward. We give it a random seed and a random one hot encoded vector, okay? And that generates an image. There you go. So we can train both. I think this is the actual. Let's see, these plots we don't need. Run, yeah, because here we start generating. So then basically, this is where we have to focus our attention now. So instantiate discriminator and generator. Okay. So the three things are detrain, detrain, and gtrain. Do you guys see that? Okay. So epoch samples. This is doing it individually, as I said, and not in batches. So if we get MNIST, the actual label, the one hot encoded version of it, and the image. And all of this is real data, right? That the image, a 7, and the one hot encoded 7, or the number 7. So we're there. So we want to train the discriminator. So this is where I need you guys to help me out. So we want to train the discriminator, right? So remember, we have to give it the real, a fake, and then do the generator thing. So detrains is the easiest. We give it a real image. We give it, let's think of it. We give it image data tensor, which is a real image, correct? And its corresponding target tensor. Yeah? Okay. And we say that it should be a 1 because that's a real. Got it? Yeah. All right. Then we generate a random, see, this is where I wasn't sure. We generate a random one hot encoded vector called random label, okay? So now we're gonna use that here. Notice this let's look at this one because it's easier, I think. So we generate a random label and we plug it in here. So the generator gets a random label. And it also gets the random seed of size 100, right? That's generate random seed. And notice we do the same thing we did before. The label that we give it is 1 because we're trying to fool the discriminator. Do you guys agree? Yeah, okay. So then the trick here is this part. This is the last actually thing. If we grasp this, then hopefully we can write the conditional GAN for batches. So now this discriminator needs to get the label 0, right? Because this is training the discriminator. We need to tell the discriminator to say that the generator produced images are fake, right? So that's 0. So what do we provide to it? The generator gets random label, which is a random label, and it gets random seed. That's it, right? Guys, so we should be able to now solve the other one. Okay, we just got to get the sizes correct. So after that, it's basically the whole process. So now let's, oh, whatever. I probably lost the GPU. Yeah, let me get a new one. So this is what all we need to do is solve this. And we should be able to have a conditional GAN working. So let me start it again. Okay, I'll get rid of this one. Okay, connect to Jupyter. Desktop. And it was MNIST CGAN. Okay, so we're trying to build that conditional GAN. Okay, so now let's go through, I guess, the logic of this one. This one, as I said, the key is that it takes batches. So let's run it again. So I'm going to do kernel, clear output. All right. So we got our libraries, parameters, batches of 32, real data, create, yeah, we can view the image, create the data loaders. Okay, so that's the trick, right? We've got the data loader is going to serve the batches of 32. So utility functions, the plot GAN losses, that should be the same. Plot metrics we don't need, plot, keep that. Random G vector input and random G batch vector input, right? So batches. This is where we were creating before. I copied this random batch. It's this one, right? We don't need this one, do we? So let's I guess we will need something. No, we don't. I don't think we need this. No. No, it's confusing. This one. All right. So this is the function, right? Random batch one hot. Let me add an RC over here. Okay. So this one generates batches of size 10 using zeros, and then we kind of inefficiently do this for loop thing, and we get the one hot encoded vectors. Okay. I'm afraid that this will be slow. Like I feel like this is going to be slow. But anyway. Okay, we know that gives us that, right? Yeah. Okay. So now we've got our generator net. So that's going to be 100 noise plus 10 to 256 to 784. Generates images. We need to give it the rand input of size 100 and the label tensors of size. The generator in the other example always took random data, correct? Yeah, always took random data. So that's what we give it. So rand input, label, cat it, and like that. So I think that's correct. I don't know if you guys see anything. Oh, sorry. The discriminator now takes in 784 batches again, and also 10. So this, when it's a real image, will take the real label, but other times it'll take random label, I believe. So 784, 10, 100, 50. This is a deep neural net. We receive the image. We receive the label tensor, right? Which could be real or fake. The key thing is we got to concatenate this correctly. All right, so it might be a good idea for us to run this outside to make sure the shapes are coming out as we need them. But I think that's also correct, actually. So then the problem may be in the training loop. So maybe you guys can. Now, these are not one hot encoded, these YBs. So we need to make them one hot encoded. Do you agree? So that's what's missing from the code is how do I make these one hot encoded? Got it? All right. So we are missing that function, but let's leave that for the aside. So we iterate this YB one hot. We need to provide that. So it's going to be some function that takes YB like that, right? So we need that. This XB was coming out as batch 1, 28 by 28. Get rid of that one dimension. We already saw that. And then it's batch by 784, right? Yeah, so we know it's 32 by 784. So that's still correct. But we need to address that. We go into G model And so let's think here. First, the real data. So this gets XB, YB. D model takes the images and the labels.
Coming from one hot and two. YB, the shape is not correct.
Yeah, we need to one hot encode it, right? Yeah, so we need to do that. We got 32 labels. We already printed it, but we need to do, so that needs to be fixed for sure. But it's what I'm missing here, right? So, but I'm just trying to check like the logic, and then we can add, we know that we add that function. So G model, to generate an image, the generator needs a random label and a random vector of size 100. Okay, so we need then here, where was it? Here, right? This one here. To generate an image for the discriminator, we need the random G vector, which we were already doing, 32 by 100. And then now we need this to be 32 by 10. Do you agree? 32 by 10? Do we have a thing that already does 32 by 10? This is 32 by 10. Right? So yeah. Okay. So that generates an image, I think. And I was doing that here, I guess. I did the same thing. So I'm just gonna comment that out. All right, so discriminator gets XB, which is correct, but YB is not one hot encoded. So that needs to be fixed. And then everything else should work. This one, D model, needs to get, so here it gets the real, now it needs to get the fake, right? So gen image still works. It's gonna be gen image here. Oh, I'm calling G model. Okay, so I already did it, I guess. Yeah. I did it here, and that's gen image, so. But then D model. This is a tricky part. D model. Oh, this is the part where we give it the same. Let me do this. This is random vector. You see that? So then there was a part in that code where we would provide this twice. So it should be, I think, like that. Do you guys see that? I remember there was a part where this was the case. Let's do rand. So rand. Okay, so real images, generated images, fake images. And this rand vector is a 32 by 10. Right? Okay, so we're done here, hopefully. And now we just got to do this one again. So random gen label. So this is the same as before, but we generate a new one. So control copy. And this is rand vector. Right? You guys see that? Because we provided only real images and real labels for the discriminator. For the other two cases, it was always fake images and fake labels, fake images and fake labels. So that's this. Now this part here then should be rand vector, the same one, right? That's intuitively what I think. Same idea. Does that make sense, guys? Making sense? So we're getting there, I think. We're getting there. So now this generates the losses. That's correct. And then that's it. So now all that's missing is the function that makes our YB one-hot encoded. How do we do that? Is there a quick and easy way to one-hot encode things, or do I have to create a function? Do you have it, Joey?
Yeah.
Let's remember it's gonna take YB, right? Which is a torch tensor,
Yeah.
and I need to make it into a one-hot encoded version of it. How does it work?
You have the capital F. I think
Yes, I do. Yeah,
So
function.
you do capital F dot one hot.
For YB?
Capital F dot one underscore hot, and then parentheses Y and then the number of classes.
Okay, so YB equal F dot one hot, one word or underscore?
Underscore.
One hot and YB is input, correct?
Yeah, and then you also give it the number of classes. So comma,
Okay.
and then classes.
Oh, I have, okay.
Yeah, you do.
Like that?
Yeah, num underscore classes equals, you know.
10. Yeah?
And,
All right.
I do a squeeze 0.
You do
I
a,
don't know if you need to or not. So then it removes one array, or one level. You try without it says.
try it like this.
Yeah, try it, see if the dimension,
Okay.
it says the dimension is like 1 and.
Okay, let's try it like this. But hopefully, if we got everything right, that should work. We were almost there. So clear output. Okay, moment of truth here. Sizes of tensors must match except in dimension 0. Expected size 100, but got size 10 for tensor number 1 in the list. This cat labeled tensor. Yeah, I think it's related to that.
Maybe print it.
Hmm?
Maybe like at that point, print YB, see what it looks like.
Yep, good idea. Could be that the concatenate I'm doing is not right. No, that's correct, right? Well, that's correct. Oh, it doesn't like. It's the cat here. Where's this cat? This is in G model. Gen image. That's where the error is, right?
Mm-hmm.
And the G model. So let's print that. That's where it's erroring out. So I thought that concatenation is the other thing I was concerned about. So it happened here. Was not able to concatenate these two. Yeah, so let's do print rand input dot shape, right? And print label tensor dot shape. Okay, let's try that. Okay, so 32,100. Yeah, so that's what it's not liking. I think it's trying to concatenate this in the wrong dimension, right? So probably dimension 1.
Yeah.
Yeah, it might be doing it by default on dimension 0. 32 by 10. Dimension 1, probably, right? I hope. So this concat function, can you guys look up this concat function to see if it has a dimension parameter? I think that's what it is. If we don't solve this, this is your homework. So let's solve it. All right, so what is it's in generator here. So that torch cat, I think it's the wrong dimension.
Oh, yeah.
Does it need a dimension?
What the Copilot says.
Dimension 1, okay.
Yeah,
Great.
you do it, you do the
Here?
tensors and, you do the tensors and oh yeah, you can, and then you do dim equals.
Dim equal 1.
Yeah.
Yeah. All right. So that kind of makes sense to me. Do we need to do this somewhere else? Do we have another torch cat in here? This one, right? Should be the same idea. Yeah. So dim equal 1. Okay. All right, so let's remove this and that print. All right, we're gonna try this one more time. Okay, no errors. Oh, okay. So there's a print statement in there that I need to remove.
Yeah, you have to.
Do I? All right, yeah, let's get rid of those.
All right. What is it? In the folder.
Forward, okay, here. No, the other one. Oh, here they are, yeah. Great. All right, so it did run though, right? So that's good. Let's start from here. Run. Yeah. Well, it's running. So we got the dimensions sorted maybe. And I think we have the logic sorted. So hopefully if that works, let's see if it prints out the loss here. And then let's just analyze this one too, because we need to know, because we will need this to generate, oh, sorry, down here, right, to generate numbers by condition. Okay, so here's the G forward. Once the model is trained, we're going to give it what? The random vector, random seed of 100. That already works, right? And then we also need to give it a tensor of size 10, correct, guys? So this one, torch 0 is 10, and then a 1 for the label should work, right? So this function, I think, will work as is, unless you guys see a problem with it. So in theory, if we did everything right, and it is doing this. So we just gotta wait now. 29 iterations. But that's a conditional again. So you can always it's 740, so this class ends at 750. But yeah, we just gotta wait for it. So just make a note of where this link is. We didn't do a conditional again in 520 for those of you that took 520. But that's the link. This code basically works and generates something like that. So you should give it a 9 and it should give you 9s, give it, a 3. So and it generates 3s. You give it a 1, give it a 1, generates 1s and so on. And that's a conditional. Yeah. Got it? So that's the objective basically. So at this point, I'm just going to wait for it to finish. Any questions? Nope. All right. So this is in theory, I'm going to let it run once it finishes. If it looks correct, I would say this is the code, the bare minimum code that you should use for your final mini project. The only complication is that I generated grayscale images. You're going to have to generate RGB images, color images. So as you know, when you add that, throws off some errors in your code, right? And then next week, we might look at Fast AI and how Fast AI does some of its GANs. And just art style transfer most likely, right? So we'll just we're towards the end of the semester. So at this point, and I might do provide a PDF for you of Stable Diffusion for you to start reading through that. We're not gonna get into that far. This is as far as I'm gonna take it, conditional GANs, but we are gonna talk about the theory of those things and look at a few examples, as I said, of Fast AI. But yeah, if you can start working on your project with this, please do so. And just generate some images of whatever thing you want to generate. Does that make sense? Any questions on the project or anything?
For the main project,
Yes.
Are we doing the CGAN with Fast AI or from PyTorch?
That's a good question. That's a good one.
It just says to use either.
Yeah, use transfer learning. It's up to you, really. I mean, I'm giving you something that's, I think, easier, and you can definitely get some images, or maybe it's harder. I don't know on this thing. Maybe Fast AI would be easier to produce actual images. But I've tried Fast AI. It's not exactly perfect either for this kind of thing.
It's limited on what you can do.
Yeah, exactly. So you have this now. Next week, I'll give you Fast AI. You can use in YOLO, for instance, when we did the YOLO example, you saw that we could bring in pre-trained models from YOLO, remember, from PyTorch. So you could maybe grab a ResNet from PyTorch and incorporate it into this. Do you see what I'm saying? That might be helpful. I don't know. It's a mini project, so you guys figure it out. But the bare minimum would be that you do this with color images of, let's say, apples and fruits. And when you say, I want an apple, it generates something that kind of looks like an apple. You see that? And if you say grapes, kind of looks like grapes, but in color. That's a good project. And then I leave it to you guys to decide. Like I said, I'll provide some examples of art style transfer next week, or Fast AI, basically. Yeah, please.
For the mini project, for the data set we choose, is this like fine tuning where you don't need a lot of data, or is this you need to get a lot of images for it?
So this, for instance, is pre-trained, right? So this is trained from scratch, and I use 60,000 MNIST images. So if you do this, then you would need a lot of images probably. If you use fast AI, it's possible that you get a pre-trained model like a ResNet and then fine tune it for something. It's up to you to figure out.
My fast AI is like 100 images, it's not bad. Cause I did.
You already did it?
I just the GAN, I didn't do a CGAN.
Oh, okay.
But I only have like 100 images.
And do they look okay?
They look like images.
Of what?
I did pixel art swords,
You did what?
a pixel art sword.
A sword.
Yeah.
Okay. Oh, pixel based, like very
Yeah.
grainy is what you mean,
Yeah,
like,
yeah.
ah, okay. And it looks like swords,
Yeah, it looks like how.
but random swords.
Yeah.
So maybe then if you're doing like a Japanese sword or, right, yeah. That would be conditional, okay. Yeah, I mean, this is the project, so you guys need to try different things, do a little bit of research. Got it? But yeah, that's the project. Yeah, like I said, I do have some notes on stable diffusion models and things like that, but we're only gonna discuss those. We're not really gonna like implement them. Yeah, that's it. I mean, I'm just waiting for this to finish. So, you know, basically I'll stop the recording at this point. I'll stay until